Autonomous vehicles have been a hot topic of conversation in the tech world for the past few decades. These vehicles would be able to get their users from point A to point B without any human intervention, which is especially attractive for users making long commutes or having lots of work to do. Many companies, including Tesla, Google, Apple, and Waymo, have all thrown their hats into the ring, creating their own versions of an autonomous vehicle and spending billions of dollars in research and development in the process. As many of these companies have learned, creating an autonomous vehicle is hard work, needing to combine aspects of image recognition, GPS location tracking, and the car's own kinematics. These vehicles also must be able to interact and navigate around other human drivers and autonomous vehicles, which if not done properly can often lead to car crashes and injuries, which is evidenced by the numerous autonomous vehicle failures that have made the news headlines over the past few years.
I'm Joshua Bruce.
I'm Colin Johnson.
I'm Suryansh Kumar.
In this video, we'll talk about what we learned in labs 1 to 3,
The flowchart we made,
And then we'll cover how we actually implemented our final project, some challenges we encountered, and a full demo of our final project.
Our lab 1 was an introduction to JetBot, Jupyter Labs, and basic robot kinematics. Firstly, we learned the basics of the JetBot itself. We learned about its hardware like the camera and the motors. After which, our next goal was to figure out basic Python programming. We used the use of kernels and how to import packages. Then, once we figured out how to get the robot moving, we saw that it would not move in a straight line. This was because of motor bias. Our next goal then became to fix this bias. After we fixed this bias, we used the values we obtained to calculate the robot kinematics. After calculating the kinematics, our next challenge was to make the robot turn left or right on an intersection. After some tries, we figured out that one motor should spin faster than the other in order for the robot to turn right or left.
Lab 2 was first about using the camera attached to the JetBot to follow the yellow line in the middle of the road using HSV values to focus on the information that is needed by the robot. Then we had to use robot kinematics and camera feedback to be able to follow the path created, a big circle in this case. This was done by feeding the heading angles of the robot to complete the turns. From there, code was created to have the robot turn to center the yellow line between the two wheels and in turn stay on the road. Next, we trained a deep learning model to recognize signs like stop signs or speed up, speed down signs. We collected many images and trained the model using said images. We then finished by testing in real time using the JetBot camera.
In Lab 3, our team learned more about communicating with a second JetBot, the CameraBot, about how to plan a path based on a starting location and an end location, and also how to locate the JetBot using the AprilTag location. Now, to begin this lab, we first started by establishing communications with the CameraBot, where we went over to the CameraBot's terminal and found the IP address of the CameraBot, which we plugged into our code, which allowed us to establish a link between them. Next, we had our JetBot send a take picture request to the CameraBot so that the CameraBot would take a picture of the JetBot that was down on the map. This took some trial and error to actually get the code to work properly, but in the end, we were able to get it to take a picture properly. After this, we moved on to AprilTag location finding, where using the AprilTag on the top of our JetBot, we were able to have our CameraBot locate the JetBot on the given map and give direct coordinates in centimeters based on where it was within the map. Finally, our team used all of this information, including communicating with the CameraBot and the AprilTag location finding, to plot a path. So we were given a map based on where we were on the board, whether we were towards the window or towards the door, we were towards the window. And then we used this map to kind of plot out, we used this map along with a number of different nodes and a number of different algorithms to figure out the shortest location between our starting point and the end point. Using this, we were able to plot a path which showed where our JetBot needed to turn and how far it needed to go. And then after this, we were able to implement a second set of code that told our JetBot whether it needed to turn left or right at the given point. While developing what we wanted our JetBot to do as a final task, our team developed a flowchart in order to easily see what subtasks we would want our JetBot to perform, as well as all the inputs and outputs that came from these subtasks. To start this flowchart, our team decided to use the get AprilTag location in order to read the current location of the JetBot so that we could start the path planning process.
To do this, our JetBot needed to send a message to the camera bot saying that it wanted the April tag location. Then after performing this subtask, the output from this subtask would be that it gets the current location based on where it is on the map. After this point, the next subtask that we wanted to do was path planning. So taking into account the pixel to real scale conversion, the robot's current pose and goal location, as well as the map image JPEG, which was the one based on the window, we were able to use our path planning code to plan the right path, which would in turn allow the robot to know what kind of distance it needed to go, as well as what kind of turns, whether it would go left, right, or continue straight. From this decision where to go left, right, or straight, we were able to implement the path following, in which we took this input decision, left, right, or straight, as well as the JetBot's own motor controls, which we extensively tested based on how the distance it was go, as well as the linear and rotational speeds of the JetBot. And finally, the JetBot's own image processing by going based on node to node based on our path plan. This would institute the path following subfunction, in which our JetBot would move from the starting location to the goal location. And the output of this would be that our JetBot reaches the goal location. And that was the end of our flowchart. It goes from the starting location where it gets the current location all the way to path following where in the end it ends up at its goal location.
After we knew what to do, we started working on the code. First, we decided to start with the basics and completed the code for the April tag and set up communication with the camera bot. Once we got the picture of the map and real-time location working, we moved on to path planning. Our goal was to ensure that the path working prints out the shortest path for any end location using the binary occupancy grid and the node population, while ensuring that the directions it spit out were the right ones.
After path testing, the next step was making the JetBot follow the path calculated. To do this, we had to write code which first calculated the heading angles. Based on those heading angles, we determined the threshold for whether a right turn, left turn, or forward motion is required. We faced some setbacks at the start when the robot would move in an incorrect manner, causing the destination to be vastly different from what was predicted. After some time, we figured out that we had to change the motor speeds so it gives the robot an ample amount of time and distance to properly follow the planned path.
As you can see, this is our successful run. The robot takes some time to figure out its starting position, end position, and the shortest path. After the command is executed, it follows the path it's supposed to. We can see it ends up in the right location even though it cuts the green part a bit. We would have loved to solve this if we had more time.
Although our project uses a small-scale JetBot rather than a full-size vehicle, it demonstrates the core principles behind autonomous driving systems by combining localization using April tags, path planning from a map, and robot kinematics for motor control. We were able to successfully guide the robot from a starting point to destination with minimal human input.
This project showed us how multiple subsections come together in order to perform autonomy. We also realized how difficult it is to make a JetBot do a simple task over and over.
Overall, while our project did not 100% succeed, we were able to get from the starting point to the end point, while still cutting a couple corners. But we were really thankful for all the learning we were able to do this semester, especially on path planning and image processing. It was really helpful for our future learning with unmanned vehicles. Overall, we just really want to thank our professors and TAs for all their help learning all this material this semester, and we're really happy with how our project turned out.
Thank you.
Thank you.